Okay, now we will discuss the Taylor and Maclaurin series. Okay, these are quite formal series defined in view of what we discussed about power series. So let me directly state the definition. Okay. A formal series, okay, for some given infinitely many times differentiable f is the series okay, where of course x0 is a fixed constant. Okay. It's called Taylor series. Of f about the point x0. Now, if x0 is 0, then it is called a Maclaurin series. Because Maclaurin series is a special form of a Taylor series, we will in general call such series a Taylor series. Now note that this series is quite easy to construct if you know what your f is. Because for the most elementary functions, we can calculate the nth derivatives and form this series. But in this form, it's not useful because we do not know if it's equal to f of x. Okay. This was a fundamental issue that we considered before. So as remarked earlier, this sum, I say sum, but it's an infinite sum. Actually, it's a limit, okay, may not be equal to f of x. Okay. So it would be quite useless for values of f, for approximations, and for all the other applications that we will discuss soon. Okay, this means, of course, that is f of x minus the partial sum will not go to 0 when n goes to infinity. Can happen. We already claimed this, so let me now show an example. Okay, consider the function okay, let me say it this way. It's e to the minus 1 over x squared if x is not 0, and 0 if x is 0. Now, as we will see, this is a peculiar looking but an extremely nice function. It's called a smooth function. That is, as we will see, all of its derivatives at 0 exist and they are 0. Okay. First of all, we immediately observe that it's a continuous function at 0 because when x approaches 0, 1 over x squared approaches infinity. So exponential of minus something going to infinity will be 0, which is the value of the function. Then, okay, if we consider the derivative at 0, that's the limit. Okay, when x goes to 0, e to the minus 1 over x squared minus 0 over x minus 0, which is, okay. Now, when x goes to 0, 1 over x may approach plus infinity or minus infinity. We will put u 1 over x to understand what's happening. Then we have e to the minus u squared over, okay, 1 over u, and the limit will be u going to, depending on the site, whether x is positive or negative, going to 0, it will go to plus or minus infinity. I don't distinguish between the two different limits because they are not different. This is the limit, u going to plus or minus infinity, u over e to the u squared. Now, clearly it's infinity over infinity form. Okay. And L'Hopital's rule says that this limit is 0. So there is a derivative at 0, and it is 0. We will not show it, but one can show that, actually, inductively, one can show that, okay, all derivatives of f exist and are 0. That's 0. Okay. So, the Taylor series would be the sum and 0 to infinity of the nth derivatives at 0 divided by n factorial x to the n. So we are expanding it around 0. Like our x0 is 0. But all derivatives at 0 are 0. But also the 0th derivative, which means the function value, namely f of 0, which was defined as the 0th derivative, is 0. F prime 0 is 0. And we calculated these. This was given. We calculated this. And Fn 0, we said by induction, can be shown to be 0. Okay. So this tells us that the series, that is f of x, which happens to be e to the minus 1 over x squared for x not 0, okay, is not this series, which happens to be 0. Because all terms are zeros in it. So this example shows that even though f has all of its derivatives at 0, okay, its Taylor series is not equal to the function except at 0, where both values are zeros. Okay. So equality to f of x of the Taylor series is not guaranteed. Now the question then remains open, that is, whether the difference between f of x and the partial sum sequence of the Taylor series goes to 0 or not. Now, we have a nice theorem which exactly calculates what this difference is. Not in a concrete form, okay, but it helps us a lot. Okay. To determine whether f of x minus the partial sum sequence goes to 0 with n, okay, we have at our disposal so-called Taylor's theorem. Okay. This theorem is a consequence of the mean value theorem that we already know from Math 119. Okay. Suppose that f, okay, is n plus 1 times differentiable in the interval AB. Then, for every x and x0 in this interval, there exists some c between them, that is, in x, x0, respectively in x0, x, if x0 is smaller or larger than x, such that the difference between f of x and the partial sum sequence is exactly the n plus first derivative at this c divided by n plus 1 factorial x minus x0 to the power n plus 1. Okay. This term, usually denoted as Rnx, is the so-called remainder term. Now, if this term goes to 0, when n approaches infinity, we have the infinite Taylor series equal to f of x. So this solves the problem. Now, to deal with this problem, at our disposal, we have a formulation. And we will be able to use it in many practical cases. Okay. Now, because it's a consequence of the mean value theorem, okay, we will give a proof of it. Okay, let us define two functions. Okay, let me write them down. Okay. The first one is the function g of t. Yeah. This is the difference over there, okay? But x0 is replaced with t. So it is f of x minus f of t plus f prime of t, x minus t, plus f double prime t over 2 factorial x minus t squared, and we continue up to the nth derivative at t divided by n factorial x minus t to the power n. And the second function is a smoothing function, if you want. This is g of t minus x minus t to the n plus 1 divided by n plus, x minus x0 to the n plus 1, g of x0. Okay. Now, these functions are clearly defined for every t in the interval ab. So they make sense if t is equal to x0, for example. Okay, when we look at these functions, we see that function f is actually g of t, okay, plus it's g of t plus a polynomial of degree n plus 1. So differentiability of f depends on differentiability of g. Now g is differentiable. Why is it differentiable? Because in g we have, t is the variable, so this is a constant. We have f of t, f prime t, we have the nth derivative of t. Now to differentiate g, we have to differentiate the nth derivative of t, of f. But f is n plus 1 times differentiable. So the nth derivative of f is differentiable. So from hypotheses, f is differentiable. In AB. Okay, and certainly continues in x0, x. Okay, I will, let me write this, respectively, x, x. Note that these are conditions of the mean value theorem. Okay, so we can apply the mean value theorem to f. In fact, we can do a little bit better than that. Let us check let us check g of x. This means that t is replaced with x because g is a function of t. So when we put x, we have here f of x minus f of x plus, now in the remaining part, we always have x minus t's. So this part is a big 0. So it is 0. But then, when you look at f of t, so f of t, f of x, again t is x, is g of x minus, well, we have x minus t here, so it is 0. Okay. But g of x was 0, So f of x is 0. Now let us look at f of x0. F of x0 is g of x0, okay, minus x minus x0. So here we put t equal to x0 now, okay, to the power n plus 1, divided by x minus x0 to the power n plus 1. So they cancel out, and we have g of x0. So it is likewise 0. So this tells us that f of x is equal to f of x0, which is 0. So actually, when we apply the mean value theorem, we are applying Rolle's theorem. Okay. Doing so, we can find a c in the interval x0, x, respectively c is in x, x0, such that f prime c is 0. Now, to see what this says, okay, let us calculate, okay, g prime of c. Okay, recalling that g of t, okay, was actually f of x minus f of t, okay, plus f prime of t, x minus t. I need these, so I will repeat a few of them. F double prime t over 2 factorial x minus t squared. And let me add another one. The third derivative over 3 factorial x minus t cubed. And it continues. This is g right away. It is the nth derivative over n factorial x minus t to the power. So the derivative happens to be 0 minus f prime t. Okay, let me maybe, still retain this. It is f prime t plus. Now here we have a product derivative. So it is, okay, f prime t f double prime t times x minus t plus, okay, f prime t times the derivative of x minus t. Now, note that t is the variable, x is a constant. For the third term, we have f triple prime t over 2 factorial x minus t squared plus, okay, the second derivative over 2 factorial x minus t, we take the derivative, times minus 1, actually times 2. Okay, that's 2x minus t times minus 1. And for the third one, similarly, we have the fourth derivative at t over 3 factorial x minus t cubed plus the third derivative divided by 3 factorial. We have here x minus t cubed, so it is 3x minus t squared times minus 1, and it continues like that. The last term here gives us the n plus first derivative at t divided by n factorial x minus t to the power n plus the nth derivative at t divided by n factorial, the derivative of x minus t to the n, which is n x minus t to the n minus 1 times minus 1. Okay, now we see that this term cancels with this one because of the minus sign. Now the second derivative, if you compare it with the second term, this is minus times this because 2's cancel out. Okay, so this cancels with this. Similarly, in each pair, the first term cancels with the second term. So here, this term cancels with this one because 3 over 3 factorial is 2 factorial. Here, you have the third derivative. You have x minus t squared, but with a minus sign. So this one cancels with this one. Similarly, this one cancels with this. What is left? Okay. Everything cancels with everything else. Okay. Only this term remains. So we have the negative, because of this minus 1, f n plus 1 t over n factorial x minus t to the n. So, f prime t is then g prime t. Okay, let us recall the definition of f. Okay, we had g of t minus the n plus first power of x minus t. So the derivative would be this one times minus 1, okay, divided by x minus x0 to the n plus 1 times g of x0. So we only differentiated this term. But g prime t, okay, was then from there the negative of f of n plus 1 at t divided by n factorial times x minus t to the n. Now, when we calculate the derivative of f, okay, because f was g of t minus a polynomial, when we differentiate these, we have g prime t minus the derivative of x minus t to the n plus 1, which is, of course, this term. Now, writing down what we have from above up to this point, okay, we see that we get f prime t equal to this difference. Now, put t equal to c. Recall, c was a value where the derivative of f was 0. So this is minus f of n plus 1 at c n factorial minus n plus 1 divided by x minus x0 to the power n plus 1. I take this term out, so I will not write that, times minus 1 times g of x0. In common parentheses, I have x minus t to the n, because it appears in both terms. Now, the left side is 0. So, I can forget this term. Finally, we get g of x0 equal to, so this term is 0 now, okay, because the left side is 0. It is equal to then, this is plus and this is minus, so it is f of n plus 1 at c divided by n factorial, but equating and dividing by n plus 1. Okay. We get this, and of course, putting this on the other side, we get this. Which of course is fn plus 1 at c over n plus 1 factorial x minus x0 to the power n plus 1. But g of x0, by definition, okay, put t is x0, okay, in the definition of the function g, it is nothing but f of x minus, okay, when t is x0, this is just the partial sum, 0 to capital N of the nth derivative at x0 over n factorial x minus x0 to the n. So it is the remainder term. Okay. As I said, shown by r and x. So, okay, r and x is the n plus first derivative at c n plus 1 factorial x minus x0 to the n plus 1. As wanted. So this finishes the proof of Taylor's theorem. It tells us what the difference between f and the partial sum sequence is. Now, this is very valuable information. Now, we are going to use this knowledge. Okay. Let the function be the exponential function. It's defined for every x, fine. Now let us form its Taylor series. Actually, it's Maclaurin series. The names are not that important. This says that, okay, you calculate the nth derivatives. So the nth derivative, okay, at 0. Well, the nth derivative of e to the x is itself. When x is 0, it is 1 for every n. Okay. So its Taylor series is the series 0 to infinity, okay, x to the n over n factorial. Now, the question is this equal to e to the x? Okay. Is f of x equal to the limit when n goes to infinity of the sum up to n x to the n over n factorial? Okay. Because this is the infinite sum, and this is our f of x, which is e to the x. Is this true? Well, you note that unlike the derivations of Taylor series for arctangent, logarithm 1 plus x, and so on, or the 1 over 1 minus x function, we did not start from an equality. In all those cases, we had an equality, geometric series. We know what it is. It's 1 over 1 minus x. And then we played with both sides. But equality was always correct. So we did not need to show it. But here, we don't know that. Here we just formed the Taylor series. We took derivatives, formed a series. Is it equal to, the infinite sum, to e to the x? Now this is the question. It should be clear that you cannot get e to the x from 1 over 1 minus x by substitution, by differentiation, or by integration. Okay. So that approach does not help here. We have to use something else, and that is Taylor's remainder term. Now, consider Taylor's remainder term. Okay, that is this one, x minus x0 to n plus first. Okay, so it is this one, where, of course, c is somewhere between x and 0. Depending on x is positive or negative, we don't care about that. So the question is, does this go to 0? Because this is exactly the difference between e to the x and this. So, okay, e to the x minus the sum up to n would be the absolute value of Rnx, which is, now, what are the derivatives here? Well, of course, the derivatives are e to the x again, so it is e to the c divided by n plus 1 factorial times x's not necessarily positive, so we have this. Now, we don't know what c is. It can change when x changes, etc., or n changes. It depends on a lot of things. But we know something. C is between 0 and x. So e to the c is bounded by e to the absolute x. Since we have c in 0x or c in x0. With this knowledge, we see that the whole thing is bounded by e to the absolute x. Now it's a constant, fixed constant, x does not change, times x to the n plus 1 over n plus 1 factorial. But this term goes to 0 when n goes to infinity by L'Hopital's rule. Here, the variable is n, so absolute x is a constant, but this is exponential divided by factorial. So the ratio goes to 0 with n, and it's true for all x. There's no dependence on x. Okay. So this says that, indeed, the error term, or the remainder term, goes to 0, and so it follows that for all x, e to the x is equal to x to the n over n. Okay, so this shows equivalence now. This time, let us consider the sine function. Okay, our x0 is still 0. Now again, it's clear that we cannot get sine x from a known equality, like geometric series, and so on, by differentiation, integration, or substitution. So we have to form the Taylor series and check, okay, what happens to the remainder term. In this case, okay, the remainder term would be the n plus first derivative at c, because there is a c between 0 and x, or x and 0. Okay? And we have this equality by Taylor's theorem. The question is, does this go to 0 when n goes to infinity? Because this is precisely the difference between the Taylor series and sine x. And this is sine x minus the sum of this. Okay. Now, let us forget this part for a minute, concentrate on this. So here, our nx in absolute value, okay, would be exactly this. The n plus first derivative at c over n plus 1 factorial, x to the n plus 1. Okay. Now, here, we observe that the n plus first derivative of sine x is not constant as in the exponential function, but it's still manageable. So consider sine 0, that of course is 0, that is f of x. Calculate, okay, f of 0. So calculate f prime 0. It's the derivative of sine x, but x is 0, so it is 1. The second derivative at 0 is the derivative of cosine x when x is 0, so it is 0. The third derivative is the derivative of this, which is minus cosine x at x equal to 0, so it is minus 1. And the fourth derivative at 0 is sine x again, so it is 0 again. Note that you can look at it either way. The derivatives, okay, repeat themselves because the fifth derivative at 0 would be again cosine x at 0. So it would be 1 and so on. Okay. That means, in short, the nth derivative, or n plus first derivative of our function, okay, is one of the following at 0. It is plus minus sine x or plus minus cosine x. It's either one of these four things. And thus, okay, fn plus 1 at 0 is less than or equal to 1 for every n. This says that our nx in absolute value is smaller than or equal to, if we look at the formula, 1 over n plus 1 factorial times x to the power n plus 1. Now, as in the previous case, x is a constant. When n goes to infinity, this goes to 0 for all x. Okay. This tells us sine x is the nth derivative at 0 over n factorial x to the n and 0 to infinity. Now, what is fn 0? We already calculated that. Okay? So we can put those things in place. Let us see what this is by looking at this side. When n is 0, f0 means sine x itself, so this is 0. Plus, when n is 1, we have the derivative here, it's 1. Okay? N is 1, and we have x. When n is 2, the second derivative is 0, so we have 0. When n is 3, okay, we have minus 1 here. And we have 3 factorial, and we have x cubed. Now, this is n is 0 case, this is n is 1, this is n is 2, this is n is 3, okay? With 4, you also have 0, because the derivative is 0. With 5, you go back to the first one. So it goes 1 again. So you have 1 over 5 factorial x to the 5th, and it continues like that. And so on. Let us continue to calculate what this is in shorter way. Let us write the right-hand side. It is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and it continues in an alternating way. Note that it only has odd powers of x. Well, this is something we expect because sine x is an odd function. Okay. So even powers, okay, are not present since sine x is an odd function. Okay. Let me, before I continue, say that this is true for all x, because the remainder term approached 0 for every x. Now, one can formulate this directly in closed form. Let us see. First of all, the powers are odd, so we have x to the 2n plus 1. We divide by that factorial. Now, be careful with this sign. The sign is positive 1, okay, when n is 0. That is with x. So it should be not minus 1 to the n, but plus 1. Okay, and this starts with, when n is 0, right, you have this. So you get that. That is, the 0th power is 1, but when you put 0, you have the first term. It's okay. If n is 1, the sign must be negative. It is negative. So this is indeed the closed form of sine x expansion. So we have equality then for every x. We showed just that. Now, let us try to obtain the Taylor series expansion of cosine x, and that it is equal to sine x.